So I thought the midterm went better. It was sort of a 10% higher average than midterm 1. Still a reasonably nice looking distribution in the top left corner. And then the histograms show the distribution of scores across all of the problems. The biggest one was, the biggest sort of wide range was obviously on question 1. But for the most part, I thought you guys got it, so congratulations. I don't know. Does anyone have any questions or want to ask me something substantive, not about brownies and machos? Everyone's okay with it? Have the grades been posted, Yukin, on BSpace? Yeah. Okay. So you can see sort of how you match up with that. And again, I'll remind you that when you look on BSpace and you see what the class grade is, or the class average grade, and it's like C+, that's obviously not right. I mean, where everything gets sort of bumped up. This is a score that says that you guys are on average kind of in the B+, A- land, right? So if you're kind of in the middle, that's sort of what the effective letter grade would have been for this exam. And then of course everything is cumulative for the whole course. So ignore what BSpace is saying in terms of what these grades translate into for letter grades. I don't take my orders from BSpace. All right, so logistics, reading, finish up 25.2 and 25.4. 25.3 is about some of the real details of spiral structure and orbits of stars within spirals, and that's just not something that I want to get into. Feel free to do that on your own time, but don't bring it into class because I don't want to hear about it. No, we're just don't have time to talk about the details of that. In general, 25 has a lot to do on galactic stellar dynamics, and there's sort of entire courses that one can take to understand spiral structure and the motions of stars in the halo and in the different thick and thin disks. We're just really not going to focus on that. 26 is about galaxy evolution and galaxy formation in general. It's a fairly short chapter. We'll be seeing a bunch of elements of chapter 26 today and then also on Thursday. And, you know, like all these chapters that we ask you to sort of breeze through, focus obviously on the sections that we cover most in lecture. Problem set 8 will be on BSpace tomorrow. You obviously don't have a problem set due tomorrow. So that's good, right? Hopefully you got a little mental space in your spring break. The Sackler lecture, the one that I advertised earlier when we talked about Sagittarius star, the black hole at the center of the Milky Way, is going to be given by Andrea Getz, and she's a professor at UCLA. She'll be here for a few days. And this is sort of one of the biggest lectures that we have every year in astronomy, and it's geared towards a fairly general audience. So I think you guys are in particular well positioned to really grasp at some of the detailed physics that she'll be presenting there. But for the most part, she's going to give you a fairly broad overview of the galactic center in a way that I obviously didn't have a great deal of time to go into. So I suggest that you do that and attend that lecture. It should be fun. And then I'm not sure exactly what the topic of her colloquium is going to be on Thursday, but she's also giving obviously more detailed colloquium on Thursday. That's in Bechtel at 5 p.m. Tomorrow. And then office hours for me, probably not today. If you want to meet with me this week, just let me know. Just send me an email. I'm happy to meet up. Okay, any questions on logistics before we move on? Everyone got it? Everyone have a good spring break? Who did the most outrageous thing? Raise your hand. You don't all know what each other did? Who thinks they did the most outrageous? Did anyone go skiing? Outrageous. Anyone go swimming? No, it's outrageous. Oh. No, I don't know. I'm just making small talk. I should probably get into lecture. So before the midterm, we had a lecture on, it's basically introducing galaxy morphology, galaxy types, galaxy properties. Remember, introduced this concept of a Hubble tuning fork that we had so-called early type galaxies, which are what we now think of as red and dead galaxies, collections of old stars, basically no star formation. These are what are called ellipticals. And as you start looking at a very spherical elliptical, and you wind up seeing other ellipticals that have more compact bulges, and you get sort of more of a ellipsoidal shape, eventually you get into sort of S0 lands, or lenticular galaxies. And that's sort of where the fork branches off, and you go up on one side and you have spiral galaxies of SA, SB, SC type, and you can also have spiral galaxies with a bar in the center, SBA, SBB, SBC. And then sort of off the fork are all the things that don't fit into this sort of grand design that Hubble devised. And those are what we called irregular galaxies. And actually, the numbers of irregulars dominate over all the other types of galaxies in the universe. It's just that they tend to be much smaller, much fainter, and so we don't pay as much attention to them when we're trying to do aggregate studies of galaxies as they evolve. But they're, as we'll see today and also on Thursday, they are quite an important component of galaxy formation and evolution. Surface brightness profiles of ellipticals and spirals. This is what's sometimes called quantitative morphology. So this is putting some real numbers to the measurements that we can make. So we have an image of an elliptical galaxy, and you say, aha, that's an elliptical, and it looks like kind of an E3 to me. Well, beyond that, what you can do is you can do the detailed measurements of the brightness of that galaxy as a function of distance from the center of that galaxy. If you do this and you sort of average over all angles phi, you wind up getting a sort of aggregate measure of the surface brightness profile of ellipticals. And remember, that was what we had a de Vogel-Lewis profile, where it looked like the surface brightness was decreasing, or numerically the number was increasing because magnitudes are all messed up, like something like r to the 1/4 power. And so it's sort of a very gentle fall off. In contrast, we said that spiral galaxies had in sort of an exponential disk profile, and we saw that much earlier on when we were just sort of counting stars and trying to understand the constituents of the Milky Way. That's sort of a generic property of disks, is that you have a lot of stars in the middle, and then the total numbers fall off very rapidly. And we said in the end that when we take an image of a galaxy and we decompose it into really sort of a disk and a bulge, we wind up seeing that decomposition fleshed out for every galaxy. And even, in the elliptical land, you might even have some sort of evidence for a small component of an exponential profile, if not be able to visualize a disk within it. So that is really all I had to say about the quantitative morphology. And that really kind of summarizes what we know and what we study, the properties of galaxies. In your upcoming problem set, you'll have a chance to sort of do some of this more qualitative morphology on different types of galaxies by going on the internet, looking at pictures. Yeah, Josh?
I have a quick question about cosmology.
Yes?
When they say island universes, is that synonymous with spiral galaxies or any kind of galaxy?
Right, so island universe is sort of an antiquated term people were using more or less 100 years ago to describe different nebulae. So nebulae are just basically little scruffs of light, so not sort of individual point sources. So nebulae describe things like where stars are formed, right? We call these star-forming regions now. Even planetary nebulae, which have nothing to do with planets, but the death of stars like our own as they become a white dwarf, those are sort of broad emission regions giving off, in this case, lots of optical light. They noticed 100 years ago that there were a bunch of things, and in fact Andromeda had been known well over 100 years earlier, that there were things that looked spiral, and they were nebula, and they were large on the sky. They were called by some island universes because we had a good sense that we lived within something that also looked generally like a spiral. And people didn't know how to understand our place in the universe outside of the Milky Way. So the universe 100 years ago was the Milky Way, right? And then we saw these things like Andromeda, and we said, maybe those are island universes. And the term galaxy, I don't know exactly where that wound up coming from, but it entered the vernacular sort of in the 1920s. And so, yes, you could consider galaxies, island universes, sort of a one-to-one mapping and just sort of changing what you called something. But for the most part, what people were looking at were spirals, because those are the types of galaxies that we see most readily and most easily. Those happen to be the ones that are big, that are nearby. Andromeda, in particular, is a very large spiral galaxy, has a larger mass than our own, and that was the sort of big island universe nearby. Okay, so I think the point, let's see, the point of Tully-Fisher relation and such was to note to you that while it's quite interesting to study galaxies and the shapes of galaxies and the relationships between these shapes of different types of galaxies, one of the great things in the utility of galaxies is our ability to use them as sort of signposts in the universe to show us, basically how the universe is expanding. That was obviously the main goal when people first studied galaxies in detail, because people were more interested in the actual constituents of those galaxies. But we now think of galaxies as a great way to measure distances. And because we can get spectra of galaxies and we can see how those spectra are different from, say, a spectrum of a star within our own Milky Way, which might be moving at sort of relative velocities to the sun of only tens of kilometers, you wind up looking at other galaxies and they're moving at 100 kilometers or thousands of kilometers or even tens of thousands of kilometers in general away from us, although Andromeda is falling into us. So these fundamental correlations of galaxies and galaxy properties are interesting in their own right, but they're really used as a means towards measuring distance. And since sort of our eyes is now on the prize to get us into cosmology, the evolution of the universe itself, we're starting to morph from trying to understand, say, spiral structure, which I say we don't really care about. Well, we do care about, but we haven't gone into great detail on, from the properties of individual galaxies to how we might use them to help us understand the universe at large. And there's a bunch of different techniques for measuring distance with galaxies. One is called surface brightness fluctuations. The other is the Tully-Fisher relation. Another called the Faber-Jackson relation. And the last is the fundamental plane. So this is more or less the subject of today's lecture, is going through these various relations. We already talked about the Tully-Fisher relation, so I'll start off with surface brightness fluctuations, just remind you what the Tully-Fisher relation is, and maybe a few other relations of spiral galaxies. And then we'll end with a discussion of elliptical galaxies. And when we say fundamental, what we're really talking about is relating observable quantities to physical quantities. So if I measure the luminosity of a spiral galaxy, I have a means to understand, say, what the size of that galaxy is in kiloparsec units, which is kind of nice because if you can measure the luminosity of something and you see how big it is on the sky, just by geometry you could figure out the distance to that object. Okay, so shall we just go over Tully-Fisher actually, just to refresh our memory what that was? Tully-Fisher related what properties to what properties? Yep. A rotation speed, brightness relation. And different spirals kind of have, on average, different scaling relations, but the typical numbers that you see is that the absolute magnitude in the B band of a spiral galaxy is something like minus 10 times the log base 10 of V max in units of kilometers a second, plus some quantity, in this case for the typical spiral like an SB, I believe you wind up getting plus 2.7. This is something, how do we figure out this relationship? First of all, this relationship doesn't have to be. Remember, we ended the class the Tuesday before the midterm with a funny statement that when we measure Vmax, well, first of all, what is Vmax? Anyone refresh my memory? Yep. So if I was going to draw a rotation curve in units of velocity and radius from the center, Vmax is this maximal rotation curve. And for a galaxy like our own, we might see something like this rotation curve, right, where we wind up having a circular velocity at large distances, and the velocities of the stars are ramping up as they go farther away. And what you saw in your midterm is that if you change the radial dependence on the density of the dark matter halo and the stars themselves, you can get different profiles. It just turns out that when you take a spectrum of a galaxy that's edge-on, you wind up seeing something that looks like this, and that's fairly universal. And what we're measuring, of course, is that on this side, we're measuring stars that are moving towards us. On this side, we might be measuring stars that are moving away from us. It depends on how you define whether your velocity is negative or positive. So it's just a blue shift or a red shift of the aggregate stars and all the motion of those stars towards you or away from you. Now, obviously, if it's edge-on, then you actually do get to measure Vmax. But if you wind up having some inclination, so you wind up looking face-on, what would the rotation curve of a face-on spiral look like? Just flat, right? It would just basically look like flat velocity, because you would see the overall bulk motion of the galaxy towards you or away from you, but this whole thing here winds up taking that part out, and so you just see zero velocity all the way across. Now, that's not actually true. You don't see this kind of bulk motion, but what you do wind up seeing is motions of stars towards you and away from you, and what you can measure is how much the stars are moving towards you or away from you as a function of distance from the center. This is very different than bulk motion, right? So if you have, say, an elliptical galaxy, it turns out there may not be any rotation at all, but there could be lots of motion inside, right? So if I took a spectrum of a bunch of particles in a jar, and I wasn't spinning the jar around, I would see more or less a thermal distribution. I'd see some of these things moving towards me or some of them moving away from me. And the overall velocity distribution, in this case it would be Maxwellian, would wind up predicting or telling me exactly what the temperature is of that system. Likewise, there's an effective temperature of stars, even in spirals. If I'm looking face-on onto a spiral, I wind up seeing some stars moving towards me and some moving away from me. And what I wind up seeing on average is just sort of a smoothing out of the aggregate spectrum of all the stars as a function of distance. Now, if the motion towards you or away from you was the same as a function of radius, what you essentially would be just measuring is the poofiness of the disk. But when we take spectra of ordinary spirals, we see this. And this is actually real data. You can decompose it for any sort of random angle and orientation of a galaxy into this. If you measure a galaxy edge-on, all you do get to measure is this rotation curve, right? And here, in this case, Vmax would be this value of about 100. Is this galaxy more massive or less massive than the Milky Way? Less massive. It's spinning less fast, right? So the velocity in interior at any radius would be less. And I haven't given you what these physical units are, but again, it's got a similar profile to the to what we measure in the Milky Way. Okay, but what we have at the top is something I haven't shown you before. This is something called velocity dispersion. So this is that measure of how fast stars are moving towards you or away from you. And what you notice is that the velocity dispersion is sort of levels off at large distances, but near the center, stars tend to be moving, there tends to be a lot of stars moving towards you very fast and many moving towards you or away from you very fast. And that's this dispersion quantity that I'll talk about later, especially when we talk about ellipticals. Yes, was there a question?
Yeah. So the Vmax is the velocity at the maximum radius, or is it the largest velocity?
It's the circular velocity. So in this case, it would be where you wind up getting out to large distances. And remember, we posited that dark matter halos had this property that at these, well, again, this is not in physical units, but assuming this is a 10 kiloparsecs out from the center, we assume that the dark matter halo is dropping off as rho to the r to the minus 2. And if it's doing that, you wind up getting this flat velocity curve. So Vmax, it's a good question, is not actually where it maxes out. It's where it sort of levels out at large distances. Good. Is there another question? I saw another hand. Okay, good. So at the top is what we call velocity dispersion. It has units of kilometers a second and is usually symbolized with a sigma. And at the bottom, its actual velocity. Clearly, there's going to be some dependence on the inclination angle. Again, if we would imagine that if the inclination is 90 degrees, you don't see any rotation. And if it's edge on, then you wind up seeing maximal rotation. Okay? So somewhere in between, there's some sort of sine I, where I might be the inclination angle. All right, so what we said about the Tully-Fisher relation is that, first of all, it didn't have to be, because this Vmax talks about and relates the mass interior at any radius. And that's more or less a dark matter statement, right? Because we know that the mass of at least the Milky Way is indeed not dominated by stars when we get out to large distances, and yet we wind up seeing these flat rotation curves. So this is a statement about dark matter. This is a statement about stars. The fact that these two things are related to each other tells us something about the relationship of how stars and dark matter co-evolve in the history of the universe. And what's interesting is that you can turn MB into some sort of luminosity in physical units, not in magnitude units, and you could relate it in units of L star or L sun. You can also take the total mass interior, M enclosed, and you could put that, say, in units of M sun. And you could play all these games and figure out sort of what the different stars are that are contributing to all this. And we can wind up coming up with some number, which was what we call the mass to light ratio. And we see that in spirals, there's about 6 times the mass divided by L of the sun. It's saying that for every sort of solar luminosity of star stuff, and this isn't exactly the luminosity as we measure it just in the B band, but the integrated luminosity, taking into account basically all the stars. For every sort of one solar luminosity of star stuff, there's 6 units of mass in these solar units. This is pretty remarkable. It's basically meaning that in spiral galaxies, we're only seeing about 1/6 of the total mass. And this jives with some of the numbers that I gave you when we talked about the Milky Way. But this tends to be pretty much true for all spiral galaxies. And the number can be between 4 and 8 or something, but this is a typical number. And I'm introducing this now because we'll see this number is different in ellipticals, and we'll see this number is actually different in clusters of galaxies next week. Okay, so if we measure the apparent magnitude of a spiral, then we have the effective distance to that using the distance modulus. And of course, that's not the thing we're trying to figure out, the distance modulus. This is a number we can measure, and apparent magnitude is a number we can measure, and combining those two is how we would wind up getting distances to that spiral. And the way this whole thing is calibrated, as we said also, is that we have to know the distance to a given spiral, whose Vmax we measure, so that we can figure out what the absolute magnitude is. And the way we do that is with Cepheids in general, pulsational variables whose luminosities we have calibrated because we can measure the periods of their brightness fluctuations. Okay, let's go into surface brightness fluctuations now. Any questions about Tully-Fisher? So surface brightness fluctuations really hinge on the idea that the surface brightness, which we called mu, is invariant to distance. So if I had a constant number of stars per parsec squared in a galaxy, in some region of a galaxy, and I looked at that galaxy close by or I looked at that galaxy far away, remember we showed before the midterm that the surface brightness would wind up being unchanged, right, regardless of its distance. What's not invariant is, in some sense, the distribution of surface brightnesses if I measured various patches of something that had the same, of a region around a galaxy that had about the same surface brightness. Let me just sort of illustrate to you what I mean by that. If I looked at a part of a galaxy, say at 20 arc seconds away from the center of that galaxy, I won't even tell you what that is in physical units. That's just some galaxy that's nearby. And I looked at 3 different patches on that, on say near a spiral arm or something. These are 3 different patches. And we'll say that the average number of stars is something like 5. So I'll put 5 in here, and I'll put 6 in here, and I'll put 4 in here. If this is 1 arc second, each of these boxes, then this is a number that I could measure as this average that would basically wind up telling me what my surface brightness is if I knew the luminosities of these things. Far away, so now I'm going to zoom out, or I'm going to pull myself back from this galaxy, but I'm going to still look in a 1 arc second box. Do I see more stars or less stars in a 1 arc second box? More stars. So maybe I see on average 50 stars. I'm just doing this for illustrative purposes, and then we'll do some of the numerics in a minute. What you see is that the fluctuations about this number, you could do it in surface brightness units, or you could do it in just counting star units. In this case is about 1. And here, this could be plus or minus 10. Let's do plus or minus 10. No, plus or minus 5. And these numbers are actually motivated by some of the theory that I'll give you in a second. This means that the fluctuations in all these different patches is something like 20%. And the fluctuations here is something like 10%. It makes sense that if you look at some screen that has a bunch of dots on it that of, say, exactly the same brightness, and you only see 3 or 4 dots on that screen, and you look at a bunch of different patches, if everything is sort of randomly distributed, you're going to see some dots look brighter, or some patches look brighter, some patches look fainter. But if you wind up looking very far away from that screen, every patch will more or less look about the same brightness. This idea that the surface brightness is invariant, but the fluctuations are going to wind up being dependent upon distance. Okay, so this whole thing of just counting stars in a little box is called the Poisson process. a Poisson process, or Poisson statistics, has this very nice property that if we look at the distribution, so now this is counting the total numbers in each of these. In this case, we might have a value of 5 as the average, and we've got some patches that have less and some patches that have more. This looks a little bit like your midterm. This is the total number. And each one of these is just counting the total number in each one of these patches. So if I look at 1,000 patches, I'm going to build up some distribution. It turns out that this number, the average number n, is related to the width. And this is what's sometimes called sigma, such that sigma is equal to the square root of the total number. So if n is equal to 100, sigma is 10. If n is equal to 10 to the 4, sigma is 10 to the 2. So what are the errors here if I wanted to plot sigma divided by n? That's 0.1. Sigma divided by n, in this case here, 0.01, right? So the more that I have, and this is the important point, the more objects that I have in this sample, the smaller I expect the distribution to be. Show you a plot of that. Oops. Where is it? Oh, there it is. Okay. Okay, so this is an illustration of surface brightness. We have some average flux of the stars. On the left-hand side is just this F bar. If I put something 3 times further away, the average flux from each individual star is 1/9 of that, right? It's just the 1 over r squared law. The density of stars, or if you want to just do counting the total number of stars in each one of these boxes, is going to be this number n. And if I move this thing 3 times further away, then because I'm looking at an area, it's basically angle squared, then I increase the total number of stars by a factor of 9. This top panel is basically an illustration of why surface brightness is constant. Right? It's the multiplication of those two numbers that winds up giving us my effective surface brightness. That's NF, right? What we do is we don't count individual stars. What we look at is the conglomeration of lots of stars within each individual pixel. And so this is what this might look like, this star here, or this galaxy here, and this galaxy over here. It's just counting up, in this case, the total numbers of stars in each of those boxes. So you see, indeed, there are bright spots where you have several stars, and there are faint spots where you basically have no stars on the left-hand side. But you notice on the right-hand side that you wind up having a similar grayscale overall if you wind up squinting at this. But you see the fluctuations are much less. Your eye can tell you this already. Now, if you sort of zoom out from all this and you're still taking an image of a reasonably nearby galaxy that you can resolve, you might have some sort of staticky looking thing where I've now zoomed out, but I'm still seeing each of the individual pixels have some fluctuation associated with it. Now, I can't see individual stars. I'm just looking at the fluctuations in individual pixels. And then I look over here, and I see that it's indeed, if you squint, you can sort of see the same grayscale, but the fluctuations are much less. And then when you do this in the context of a blurry atmosphere, you still see the same effect. Much brighter spots, much fainter spots. And this is a statistical measure of fluctuation. So you find out what the overall surface brightness is, you measure what that fluctuation is in each individual pixel about the average, and then you have some measure of sigma divided by n. Any questions about that? Everyone see that sort of illustration make sense to you in terms of fluctuations? All right, so now let's turn that into a measure of distance. the sigma of the surface brightness divided by the surface brightness, or mu, is just sigma of the stars divided by the total number of stars. This is just square root of the number of stars divided by the number of stars. And this is just 1 divided by the number of stars. So this is something that we can measure, and this can wind up giving us some sort of hint of the total number of stars in some patch. If I solve for the total number of stars in these quantities right here, the total number of stars, I'm going to just square this. I wind up getting mu divided by sigma of the surface brightness squared. This is measurable. This is measurable. And what does that wind up telling us? It means that I can infer what the total number of stars are in some little patch without knowing the distance. So I essentially can have a sense of what the total numbers of stars are. And if I know how stars are distributed in their masses, etc., I can wind up inferring what the absolute luminosity is of those patches, which means that I can figure out what the absolute magnitude is. And if I can measure the magnitude of one of these patches, this is measurable. And this is also measurable. If I can infer that from things I can measure, and I can measure this, then I can get the distance. Sounds a little bit convoluted, yeah.
When you said the standard deviation was equal to the square root of the number of stars,
Yeah.
you don't have to say that it's equal to the square root of the average number of stars?
Yeah, I've gotten rid of the average. But yes, you can do averages on all of these if you want. Right? Yes?
Doesn't this rely on the assumption that all the stars have the same brightness?
Yes and no. I mean, you can do this where what you do have to assume is that stars have the same distribution of luminosities as the Milky Way does. And that's not a bad assumption. You can actually kind of show that holds. But you're right. In detail, this thing gets quite complicated if you're actually trying to work this out. And what you can do at best is get a measure, sort of a statistical measure of what the distance is of that galaxy. But you don't get an exact measurement of this. It's purely a statistical thing in the same way that sort of statistical parallax or kinematic parallax was. There's going to be some uncertainty associated with that. And it's not just in the measurable quantities, because we might not measure these quantities exactly. There's also that sort of systematic uncertainty of the fact that we don't know exactly how the stars are distributed in that galaxy. Okay, so really just using statistics and some underlying assumptions about the distribution of stars as a function of their intrinsic luminosity, you can get a measurement of distances to different galaxies. And that's sort of pretty nice. But of course, you have to be able to resolve large patches of that galaxy. And that galaxy has to be near enough by that if I look at a galaxy and it looks like this from a little part of the sky, that huge galaxy is going to be, just massive, right? So it's got to be actually fairly nearby for this technique to work. So generally within tens of megaparsecs, one can use surface brightness fluctuations as a technique to measure distance. All right. There's another relationship that I just wanted to mention. Were there any other questions?
Say tens of megaparsecs. How far is that? Like, say, how far is Andromeda?
Andromeda is a megaparsec. Well, it's 770 kiloparsecs, but yeah. Factors of 10 to 100 larger than the group of galaxies that the Milky Way resides in. So one last relationship of spirals is that log base 10 of a quantity called R25, which I'll define in a second, is equal to minus 0.249 times the absolute magnitude of a spiral minus 4.00. And here R of 25 is the radius in units of kiloparsecs at which the surface brightness is equal to 25 magnitudes per square arc second. And MB, of course, is the absolute magnitude. What does this say? If this number is very small, that is, the thing is very bright, then I have a negative, well, I go more negative inside. I go more negative here. I multiply by a negative number here. This number gets larger. So log 10 of this radius is getting larger the more negative I go. Yeah?
What units is R25?
Right. So that's in units of kiloparsecs. What does this mean? Pretty obvious. Bright spirals are bigger. Like, duh, right? But again, that didn't have to be the case. This relation is actually fairly tight. Somebody only, sort of decade and a half ago realized that this relationship was actually as tight as it is. And that's because you need a large number of spiral galaxies whose distances you can infer this, and then you can wind up inferring this. And these are very complicated, detailed measurements that one has to make to get this right. But it's fairly remarkable because, again, it's saying that the size, in this case, the overall distribution of stars, which, again, is also related to dark matter, is going to be related to the total numbers of stars you have. It may seem obvious that big things are brighter, but it really didn't have to be that way. And yet it is. Okay, let's talk a little bit about ellipticals now. Were there any questions about spiral relations? Okay. Yeah, I want to talk a little bit about ellipticals and just sort of remind you about the orbits of stars within ellipticals. That the stellar orbits are kind of like the bulge of the Milky Way, in that you have sort of non-ordered motion unlike spirals, which have some overall angular momentum associated with the entire system, there is no appreciable angular momentum in ellipticals. Again, I come back to this concept of a swarm of bees. Think about a swarm of bees just all sort of moving. If you zoomed in on this system, what you would see is that each individual bee would more or less be just moving in its own orbit around the, in this case, the center of the swarm. So stars are moving in basically random orbits. In ellipticals. Now, it's not exactly true. As I showed you in a dwarf elliptical, there was a little bit of dust and there may be a little hint of some sort of ordered motion in the form of a disk. But for the most part, when you look at sort of the classic ellipticals, there is no sort of conglomeration even of stars. It's not like we have, apart from globular clusters, we don't have smaller structures that are kind of all moving en masse and all moving around, say, the center together. The total kinetic energy, of course, if we sum up over all of these, is going to be 1/2 mass of each individual star times the velocity squared of each individual star, where I is going to go from star 1 to star n. The total potential energy, capital U, is for a spherical system is minus 3/5 gm squared over r. This is the potential energy of a spherical galaxy. I think you've shown that in 7a. If you haven't, go through the derivation again to see where this 3/5 come from. Obviously, in a unit sense, it has to go like gm squared over r, because the only r that's relevant is some sort of overall size structure, size of the elliptical. The only masses that are involved are the overall masses, right? And why is that the case? Why is it that there are random orbits? It's because of the formation of how ellipticals come to be. We think that ellipticals are sort of form in the deep potential wells of galaxy groups. And in a galaxy group like our own, we have two large spirals. And eventually, the Milky Way and Andromeda will collide. Not that the individual stars will hit each other, but they will actually wind up passing by each other. And the potential that a star which was originally bound to the Milky Way, say the sun, feels will all of a sudden be completely perturbed by this incoming potential, right? So that star just says, ooh, I don't know where I'm going to go. I'm just going to fly off in a random direction. I mean, I'm obviously oversimplifying. What you can do is make movies of how galaxies collide in groups, and you can actually watch the individual orbits of individual stars. Or, because what's most important is not how the stars move, because that's not what defines the potential, it's how the dark matter sort of sloshes around within that potential. You can see what you wind up getting in the end. So let me show you a little movie that's from a supercomputer simulation of a bunch of stars that are all conglomerating and accreting each other. And you see a bunch of satellites. You see a big spiral just came in. And what we're watching is where the mass is. And of course, the stars decide to go where the mass is, because that's where the gas is, and that's how they're going to fall. So over time, you might see a group, and I'll play it again, where we started off with just a bunch of spirals. Those spirals all wind up merging. You see another one come in. It gets completely disrupted. It does. Next time. I'll do more of these things when we talk about galaxy growth. And in the end, what you have is an elliptical galaxy. Okay, and if you actually follow the orbits of these things, just basically using gravity, you're just using Newtonian gravity, and you just watch how every star is interacting gravitationally with every other star, and every parcel of dark matter is interacting with every other parcel of dark matter, you wind up seeing these sort of large ellipticals grow over time. And if you use all the gas, because things are smashing into each other and you're compressing the gas, you wind up getting bursts of star formation during these major merger activities. And then the star formation subsides. And over, say, 10 billion years, if you started off with these little spirals and they wind up merging and all the little dwarf galaxies around them, you wind up using up all your gas. And all that you have left is more or less a dominant elliptical and perhaps a couple other satellites around it. Was there a question? Yeah.
So do ellipticals ever settle back down into spirals? Or, like, because it seems like if they just form because of perturbations of the potential. So once there's no more collisions, wouldn't it settle back down into the spiral?
Well, so we'll talk a bit about that later, because there were some ideas of what's called a top-down galaxy formation, where you started with large systems, like a large elliptical, or just say a large amount of mass, and you just sort of watch how it all winds up collapsing into a pancake, because you have maybe some gross overall angular momentum. It's just not the case. So we'll talk at length about why that's not true, but in general, it doesn't look like ellipticals then sort of somehow transform into sort of flattened pancakes that turn into spirals. First of all, we think that gas is an important component of keeping a spiral structure going, even though it doesn't necessarily make up the full amount of the mass. And that's because if you have large gas parcels, or clouds of gas that are falling through a protodisk, it has a really good chance of getting stopped by that disk because of the other gas that's already congregated there. So if you don't have anything to stop sort of a parcel of gas from going through a disk, it just keeps on going, in which case its orbits never really sort of circularized, right? It doesn't have a chance to dissipate the kinetic energy. To get flattened pancakes, you have to dissipate kinetic energy, and without gas, it's really hard to do that. It's not at all, I mean, that's not at all an obvious or, explicitly quantitative statement. That's more or less a qualitative thing that people are starting to recognize is fairly universal. But it's a question that people have been asking for a while, so it's a good one. Okay. So let's look at the motion of each individual particle and then see how we might relate the overall motion of an individual particle to the bulk motion of what we might see by taking a spectrum of that system. I can choose, if I posit that I indeed do have random orbits, I can choose a coordinate system where x is going to the right and y is coming out of the board and z is going up. And I can just say that the velocity of this particle is some v vector within this system. I'm just looking now at one particle. So velocity squared of that particle is just going to be vx, vy, vz, the component of the velocity in the x direction, and the y direction, and the z direction, dot product vy, vz. And this is now a little bit of a trick. So this is obviously just vx squared plus vy squared plus vz squared. Yes?
Sorry, can we put x coming out? I don't know, it's really bothering me that x crosses y doesn't.
You happier? You don't like, you do this? Is that how you guys greet each other when you see each other? No. Okay, sorry. The good thing is this is an audio-only class, so no one captured that on video. If we want to know the average of this quantity, because that's going to allow us to start figuring out what the total kinetic energy, I'll drop the subscript of I'll leave the subscript of the particle. That's going to be the average of vx squared plus vy squared plus vz squared. And here's where a little bit of the trick comes in. If these are truly random orbits, and I can truly go like this, or I can do this with my left hand, doesn't really matter how I define what the motions are, right? So what must be the case if they truly are random motions is that vx, the average of vx squared, the average of vy squared, the average of vz squared are all the same, right? Because there is nothing natural about what vx is relative to the vy. So these all have to be about the same. 3 times vx squared, average of vx squared. Everyone agree with that? If not, you're wrong. No, I mean, if not, ask me. Okay, so what is vx squared and how would we actually measure that? Well, that's the average squared of the velocity in this direction, in the x direction, if I'm pointing this way, and also taking into account the motions in that direction there, right? So there's some overall velocity associated with that. Now, what if I decide to orient my x-axis so that it's in the radial direction pointing towards you as an observer with your spectrograph? Then we might just call it vr squared. So now it's the motion towards you or away from you from some random elliptical galaxy. What's wrong with that, right? That could be x. That's fine. And this is something that we can actually measure. This is what's typically called sigma squared. And if we're going to try to measure that in detail, here's my elliptical galaxy. Here's a spectrographic slit that I put across that galaxy. This is how we actually might observe this. And as a function of radius away from the center, what I'm going to do is more or less measure at any one of these distances along the slit a aggregate spectrum of everything here. Now, I don't have a lot of gas, so what I'm measuring is the integrated motion and the integrated spectrum of all the stars moving towards me or away from me. Think about this thing as an ellipsoid. Think about measuring, sort of taking a little core sample through this galaxy and looking at each individual star. So some stars are going to be moving towards the center, some will be moving away, right? In which case their effective Doppler shift will be 0 relative to me. Some will be moving directly towards me, and some will be moving directly away from me. If I'm now integrating up the overall spectrum of all those stars, I'm going to wind up seeing an overall Doppler shift. And like sort of thermal broadening, when we talked about the kind of shape we might see of, say, a 21 centimeter absorption line through a cloud of neutral hydrogen, we wind up seeing some sort of overall broadening, which is related to this velocity. So if I made a measurement at this location here of the flux as a function of wavelength, I wind up seeing some overall spectrum. And that spectrum will look more or less like a red star, except for the fact that it's not going to look exactly like that if I zoom into some little region right here. I'm not giving you any of the units here, but this is basically in the optical part of the spectrum. If we wind up zooming in here, what an individual star might look like is have some sort of jagged lines, but we wind up sort of broadening all that out. So an individual star, let's say just for illustrative purposes that this elliptical galaxy is made up of only of F stars, and they're all exactly the same F star. It's actually not too unreasonable. Then the spectrum that I would see if there was no motion towards me or away from me would be just the spectrum of lots of F stars, which would just look like the spectrum of an F star. But because some are moving towards me and some are moving away from me, I have some overall sort of smoothing, right? And this is a sense of a thermal broadening. But in this case, it's that smoothing which I can measure is this what's called this velocity dispersion. I more or less just take, if you want to think about it, I take a filter and I just smooth this out by some sort of velocity, where now the velocity of the smoothing is just going to be related to delta lambda divided by lambda times this quantity c. Okay? So this is how you would measure this. And this is now what this average velocity squared must be, is something that we can measure. It's going to be 3 times that value that we can measure. Okay? If this system is not collapsing and it's not expanding, it's in virial equilibrium. If that's the case, then minus 2 times the average kinetic energy is equal to minus the average potential energy. So 2 times 1/2. If I'm now going to say every particle has the same mass and we're going to have the same velocity or average velocity, I can just call this the total mass of the elliptical. So not in each individual particle. I'm just going to sum over that. V squared is equal to 3/5 gm squared over r. This means that sigma squared, the 3's are going to wind up canceling, is just gm divided by 5 times r, where I'm now going to subscript r with something called r effective. It's an effective radius. And you can define the effective radius in kiloparsecs units, or the radius at which the surface brightness falls to some number. But the point is that the velocity dispersion is directly proportional to the mass. So we haven't yet talked about the luminosities involved with the stars that are moving in these random orbits. But now what we can do is try to understand, given a surface brightness profile, how we might relate the surface brightness that we observe to an overall mass of an elliptical. And what we'll see is something fairly surprising. Any questions before I go on? This is what's called the Faber-Jackson relation. Sandy Faber is an active researcher at UC Santa Cruz. She was the main author of this paper that discovered this relation. Remember, we talked about sort of physical units of surface brightness, not in magnitudes, but in, say, watts per meter squared per steradian. And if we posit that the surface brightness has some value, it's some sort of constant value, call it IE or IE0, this is going to be related to the flux from some, here's our elliptical, here's our little patch right here. We're going to wind up getting some size, some distance d, and some angle of that patch is going to be theta, just giving you some of these numbers. The flux from all of that is going to be divided by the theta squared, which is going to give us these units. This is just the luminosity of all the stuff in that patch divided by 4 pi d squared theta squared. And if I call this sort of size r, clearly theta is r divided by d, distance to the source. If I now don't think about this as some sort of patch, but I think about this as some distance, r is now a distance from the center here, what we wind up seeing, of course, is that I can use this r as an r effective, and I can relate the velocity dispersion to a mass. I'll get to that in a second. So this I is going to equal L divided by 4 pi. I can now put in L divided by 4 pi r squared, where I've now put in this r to substitute this d times theta. I'll put in an r effective of gm divided by 5 sigma squared, all quantity squared. And just to sort of carry through various units, I get 25 L sigma to the 4th, 4 pi g squared m squared. And this is usually written as 25 L sigma to the 4th divided by 4 pi g squared kappa squared L squared, where I define the mass. This is now mass, not absolute magnitude, is equal to mass divided by luminosity times luminosity, and this is this quantity kappa. This ml is something I've already showed you. This is the mass to light ratio. So if I substitute this in, it allows me to use the mass to light ratio, and I wind up seeing that the luminosity is going to go like sigma to the 4th divided by this quantity EI, 25 divided by 4 pi g squared kappa squared. It's a little trick to say that the mass is going to be related to the luminosity by some number. if that's the case, it should be clear that if the mass is related to luminosity by some number, there's going to be a relationship between sigma and luminosity. Here is the Faber-Jackson relation from the original paper. It's a fairly remarkable result. It shows that as I get to brighter ellipticals, I wind up having larger, not velocity in a rotation sense, but a dispersion sense. And here, unfortunately, they used a V instead of a sigma, which is now more common. But that line that you see right there is luminosity. This is basically a statement about luminosity, and this is sigma. It winds up going like the sigma to the fourth power. So there's a very strong relationship between the luminosity of an elliptical and that of its apparent velocity dispersion. Now, it turns out there's a couple of sort of cheating steps in here, in particular assuming that the mass to light ratio is constant. And actually, if you're paying attention, I also had to assume that the surface brightness was constant within this R effective, and you know that that's not exactly the case. So people have been pushing on this Faber-Jackson relation for a while to try to understand why this has to be approximately true. And you see that there's actually some dispersion about that line. It's not all those dots don't fall on that line. And maybe even some of these galaxies are completely inconsistent with that line. It's still remarkable because it goes over several orders of magnitude in the luminosity. But what people have realized is that there's a way to relate the effective radius, the velocity dispersion, and the surface brightness together. So I remember I sort of assumed that surface brightness was constant. But the observations show that this effective radius is proportional to sigma to the 1.24 I effective. So this is, again, some radius at some effective surface brightness, and this is that effective surface brightness to the minus 0.82. This is what's observed. This is sometimes called the fundamental plane. And this relationship wasn't found until the 1980s, where it was shown that if you take the effective radius in units of kiloparsecs, and you take some strange little quantity that involves the surface brightness here and the velocity dispersion, you get a line in this weird space, which is very, very tight. That's why it's called the fundamental plane, because it looks like it appears to be fundamental. It looks like, regardless of the type of elliptical that we're looking at, this works even for dwarf ellipticals, not just giant ellipticals. Regardless of their size, regardless of their surface brightness, and regardless of their velocity dispersion, they have this relationship between these three parameters that's just observed to be true. And it's called a plane because if I have a line that connects the dots in 2 dimensions, we call that a line. If we have a line or we have something that connects the dots in 3 dimensions, that's a plane. So what you're looking at is really a projection from 3 dimensions, these parameters, into what's constructed into a 2-dimensional space. Doesn't matter that you understand the details of that, but I wanted you to understand that there is an observed relationship between all of these quantities. However, if sigma squared is proportional to the mass divided by R effective, and the luminosity is proportional to R effective squared times IE, which is proportional to sigma to the 4th, then sigma squared is equal to kappa RE squared IE. I'm not going to go through all the algebra here, divided by RE, which means that this effective radius goes like IE to the minus 1, kappa to the minus 1, sigma squared. Effective. if we compare these two, what we see is that kappa has to have some dependence on sigma and actually IE to absorb this. What you see is that kappa has to go like sigma to the 3/4, IE to the minus 0.18. And if you put in the numbers for luminosity, you'll see that that kappa has to go like luminosity to the 3/16. It's not important that you understand exactly why this all comes about, but one of the things that's quite important to understand is that kappa, which again is the mass to light ratio, goes very weakly like luminosity. And if it doesn't, then this fundamental plane doesn't work and isn't as tight as it is. We don't understand why the fundamental plane exists, especially given the fact that you saw that the buildup of ellipticals is probably related to the merger of lots of random galaxies with their own sets of stars, with their own initial trajectories. And yet, somehow, these virialized systems that have basically random orbits like to fall down into this and relax onto this, this relationship. And to do that, the mass to light ratio has to go like the luminosity from the stars to the 3/16th power. Spooky. Luminosity is going to be related to mass. So it means that the larger the mass I go in ellipticals, the more dark matter there is. And the typical numbers that you wind up seeing for a kappa is something like, say, 20 to up to 100 in units of solar units. And what did I say for spirals? It was sort of 6 to 10. So there's something crazy about this. It means that there's a lot of dark matter. For every one star that you see, there's a lot of dark matter that is clearly there because we can measure it dynamically. And again, dynamics isn't now the motion of spiral arms, but it's from the velocity dispersion. And elliptical galaxies basically have to be dark matter dominated. We don't really understand that. But you can sort of get a sense if you think about those simulations that you've got these big pools of dark matter, you've got sort of the stars all falling into these large pools. Eventually everything's going to want to settle down into a large potential. And so it kind of makes sense. We're talking about motions of stars on large scales in the presence of dark matter. What's really strange, and this is even newer than the fundamental plane measurements, is this relation, which was found, I think, in 2005. And this is that the velocity dispersion of not just elliptical galaxies, but the bulges of even spiral galaxies. So more or less, large conglomerations of systems that have random orbits, is related to the mass of the black hole at the very center of that galaxy. So this is a different kind of dark matter, not dark matter in a missing matter sense, but now you're talking about something which is 10 to the 6 to 10 to the 8 or 10 to the 9 solar masses, obviously very compact at the centers of individual galaxies. And we think that basically every galaxy harbors a black hole of some mass. And there's an incredibly strong relationship between the overall motion of all the stars at tens of kiloparsecs away from that black hole and the mass of that black hole. We really, really don't understand this, because the sphere of influence of a even very large black hole is only of order parsecs. So that means that if you have the orbit of a star and it winds up passing at close distance 100 parsecs away, it won't even notice the presence of that black hole because there's too many other stars interior, and the mass of those stars dominates over the mass of that black hole. So you go a kiloparsec away or 10 kiloparsecs away, those stars should have no knowledge of the black hole at the center, and yet it really looks like they do. Anyone want to hypothesize what people hypothesize about this? Yeah.
Well, the mass of the black hole probably depends on how many galaxies, because the black hole, supermassive black holes are theorized to be resultant from collisions of other galaxies, right? So maybe.
Well, what do you mean collisions of other galaxies?
Like how many galaxies, or lots of mass colliding into
Well, if you look at, I think you're on the right track, but just a point here is that if you look at stars in one galaxy interacting with stars in another galaxy, when they actually merge, the stars actually never touch each other. They only interact gravitationally. So and then all they wind up really doing is just sort of perturbing orbit. So they never actually fall into each other.
Yeah, I just remember reading something in the book in Go and Honestly saying that they think that supermassive black holes at the center of galaxies are resulting from like intersections of galaxies. I don't know.
It's related to that. It's thought that every little sort of dwarf galaxy, or something a little bit larger than a dwarf, has some little seed black hole in it, maybe 1,000 solar masses or 10,000 solar masses. Where that came from, we don't know. But if you play the movie backwards, you look at all these little galaxies, these building blocks, they have their own black hole. These things merge. There's actually gas involved when the mergers happen farther back in time. The black holes, now we have 2 black holes in our system after the merge. They wind up settling down and they wind up coalescing, actually sort of giving off lots of gravity waves. And you wind up getting a bigger black hole. So it's black hole mergers that make bigger black holes, we think.
Well, then maybe the mass of the black hole correlates with the amount of dark matter, and that's
Maybe, yeah. So people think that there's some relationship between the masses of seed black holes at the centers of these sort of weak potential wells early on in the history of the universe. And if you start off with that and you play the movie forward, you look at lots of mergers, and it makes sense that these things might be connected. What also is very likely at play is the fact that black holes at the centers of galaxies can turn on, they can light up as in the form of quasars. And when you have these massive quasars which are putting out a lot of light, there's a tremendous amount of energy that's coming out of these black holes. So you have all this matter accreted. Some of it that makes it actually into the black hole, but some of it actually gets spit out in the form of jets. Those jets have a lot of kinetic energy associated with them. And it could be that if you have a really very large black hole, the kinetic energy of the stuff that's coming out could actually quench merging of other galaxies onto that. It may have that much strength. In which case, a black hole sort of says, no, I'm already big enough. I don't want to merge with something else, right? And so could be some sort of negative feedback where the bigger the black hole, the less small mass it's willing to take on, and you need a very big mass to sort of jump that black hole up into a larger mass. This is all very speculative, but and people are still sort of trying to understand why these galaxies which fall off that relation are actually there. The Milky Way, by the way, is somewhere around here. Here it is, right here, Milky Way. Oh, why? So why isn't this number 220 for the Milky Way? Velocity dispersion, that's right. It's the motion, the average motion of stars back and forth, above and below the disk, if you like, or the random velocities that aren't associated with the motion of that disk, those are completely different. All right, so I'll end with that, and then what we'll pick up with on Thursday is a discussion of galaxy formation and galaxy evolution. We'll talk about how many galaxies there are of different types, and we'll start thinking about the distribution of galaxies in the universe.